Over time, the Philippines has gradually changed from an agrarian to an industrial and service-oriented economy. With the emerging technologies and technological improvement of the country, the industrial sector came to light and became the engine of the economy with ease. In line with the change, manufacturing companies were built and offered a lot of job opportunities to Filipinos. But, as a consequence, the environment suffered from plenty of pollution, one of which is water pollution. In the Philippines, water contamination is considered as one of the serious issues that needs to be taken care of. Millions of Filipinos rely on unsafe drinking water supplies and, out of 127 freshwater bodies that they conducted a study, only 47% are of good water quality. One of the top contributors to this pollution is the industrial wastewater that came from the effluents produced by different manufacturing companies. The kind of pollutants varies according to the type of companies involved, but the most common are the heavy metals. Heavy metals are present in the bodies of water, but a lot of them are toxic even in very low concentration. These usually enter the human body through food, especially when consuming fishes that live in infected bodies of water. Various health risks are associated with heavy metals toxicity, such as lower energy levels and conflicts to the major parts of the body. Long exposure to such can lead to some gradually progressing diseases like Parkinson's disease and Alzheimer's disease, and repetitive exposure can cause cancer. To prevent this, the DANR sets standards for the heavy metal concentration of the effluents that will be released in any body of water. Currently, they conduct monitoring of the heavy metal content of different bodies of water. Their method of monitoring includes sampling and laboratory testing. However, every process is done manually, which makes it a tedious process that consumes a lot of time and effort to be done. In line with this, the group proposes a device that would reduce the sampling and testing time to few minutes from 15 days of processing. The device will also decrease the expense of the government for the travel to the samples from the sampling location and laboratory testing.
The study intends to design and develop a portable floating system that will determine the concentration of the selected heavy metals such as lead, cadmium, and copper in a body of water and provide a printed copy of the results. Specifically, the study aims to 1. Design a floating mechanism that is composed of a remote control which allows the user to navigate the device to the sampling point, sampling acquisition mechanism that will acquire the water samples needed, a part of the detector that will use spectroscopy to obtain the wavelength of the acquired sample, and a data transceiver that will be responsible for the onshore and offshore communication. 2. Develop the water sample acquisition system with integrated spectral triad sensor and toolkits that will acquire 1 liter of water samples from the sampling point, extract the wavelengths of the water sample, and build a dataset that will be used for training and validation of the system. 3. To perform an experiment to determine the wavelength of the heavy metals needed for the machine learning. 4. To train the 3 classification and 3 regression machine learning models and choose the best model that will determine the presence and concentration level of cadmium, copper, and lead. 5. To create a graphical user interface that will provide the concentration level in milligrams per liter of cadmium, copper, and lead in a bar graph representation, the date and time of the testing, the location of the sampling point, the assessment of each concentration level, and the status of the offshore and its battery level. 6. To evaluate the accuracy and reliability of the whole system through series of testing.
The proposed system is a portable device that can travel in large areas of lakes where it automatically collects water samples containing toxic heavy metals, namely lead, copper, and cadmium, at a specific location of the sampling point based from historical sampling documents provided by LLDA. The acquired water samples are placed in a sampling container and will be examined using the process of spectroscopy to determine the selected heavy metal and define its concentration. The outcome will then be evaluated using the guidelines of water quality for secondary parameters, metals that are provided by DENR. The system contains two devices, namely offshore device and onshore device, and it is subdivided into 6 parts: sampling point navigation, water sample collection, data acquisition, data transmission, machine learning, and output display. The system offshore device is designed with buoyancy similar to the boats. It consists of two identical design boats attached with braces to attain greater stability. The hardware for the data acquisition is placed on an enclosure and it is between the centers of two sides of two boats. The customized boat will be deployed in Laguna Lake that is near the industrial companies. The offshore device contains Arduino microcontroller for processing the set of instruction and manipulation of the sensors and modules, spectral triad sensors for the process of spectroscopy and data acquisition, LoRaWAN, transceiver radio module for data transmission over long range, GPS module for guided navigation of the offshore device, water pumping device for water sample acquisition, DC motor installed with propeller for movement of the offshore device in area of lakes, and sample container for storage of water samples. The system onshore device serves as the main controller of the offshore system. It is operated to control the movement of the device in the area of the lake and to display the result of the testing. LCD touchscreen will operate to present the user-friendly graphical user interface of the system to provide controls of the system and the necessary information. The device contains a Raspberry Pi which will run a Python software for machine learning application. And with Python's inbuilt GUI toolkit, it also contains an Arduino microcontroller and LoRaWAN transceiver radio module for the transmission of instruction of the offshore device and reception of the information from the spectral triad. Upon displaying the output results, the thermal printer is used to print out simple information of the examined samples. Using Python software, the system will utilize machine learning for classifying the heavy metal present and predicting concentration level of each heavy metal present. For the classification algorithm, the group will use artificial neural network, support vector machine, and k-nearest neighbor. For predicting concentration, regression algorithms to be used are artificial neural network regression, support vector regression, and k-nearest regression.
The process starts with the user navigating the offshore device to the sampling location using the GUI shown on the 7TFT display in the onshore device. The communication of these devices is through the LoRaWAN module. Once the location is selected, the acquisition of water samples will proceed using the roller for the hose and the water pump. Then, using the spectral triad, the absorbance level of the water for the 18 wavelengths will be measured and transmitted back to the onshore device where the detection and measurement of concentration will take place through machine learning. For the detection, 3 classification machine learning models of the same algorithms will be used, one for each metal. This will be the same for the measurement, but this will use regression instead. After this, the concentration level in milligram per liter will be displayed in the TFT screen, as well as the assessment based on the DNR standards. Also, a printed copy of the result will be given using the thermal printer. The onshore device is designed to be handheld by the user because it will act as the controller of the offshore device. With that in mind, the proponents designed a small box-like casing made of light plastic with a TFT display located on the top and the switch in the front. This houses the Arduino, Raspberry Pi, LoRaWAN module, and step-down regulators. Also, since this is a wireless device, a LiPo battery with 2200 mAh is included inside as the supply. The proponents consider different kinds of factors upon designing the prototype of the offshore device, such as stability and the total mass that it can handle, and the isolation and insulation of the system. The main concern of the proponents was its stability because upon deploying it on bodies of water, it needs to withstand the waves and wind. To assure the stability, the prototype was built with two large bases of stainless steel. The batteries were positioned at the middle so that it will serve as the balancing weight. The main system is located in a sealed container that is fully insulated and covered to avoid any liquid substance to enter that will cause any problem to the circuit. There is also a separate completely sealed black container which blocks any light that might enter, located at the back for the water sample and data acquisition.
This is the homepage GUI of the system. Three buttons are present in this window: the Select Location, Help, and About buttons. The battery level is also shown. To start the process, the user needs to navigate the system to the sampling location. The navigation and the location map will be shown after the Select Location button is pressed. The figure shows the navigation window and it displays the arrow keys that will control the direction of the movement of the boat, as well as the select button that will start the sampling and testing of the system. After pressing the select button, a loading screen, as shown in the figure, is displayed to indicate that the sampling and testing is taking place. Once done, the results will be viewed in the output window. The said window displays date and place of testing, the concentration level of the heavy metals, and the assessment for each heavy metal result in accordance to the DENR Administrative Order number 2016-08. A print button is also present in the window to print the receipt of the testing.
The dataset is to be acquired from a laboratory experiment which will determine the wavelength that will be used for testing and verification of the results. However, due to the COVID outbreak, the proponents were unable to perform the experiment. The wavelengths used is assumed since there are quarantine restrictions implemented including Luzon. A dummy dataset for both the classification and regression machine learning model was created. It was obtained by generating random numbers via Microsoft Excel. Each heavy metal has a model for classification and one for regression. With that, the system will have a total of 6 models, 3 classification model algorithms and 3 regression model algorithms. Through the process of training for each learning algorithm, the best parameters for each algorithm will be acquired through the use of grid search with varying data splitting. After a series of training and testing, the final classification machine learning model to be used and the respective data split are ANN with 80-20 data split for cadmium and SBM with 80-20 for both copper and lead. For regression, the final machine learning is KNN with 80-20 data split for the 3 heavy metals. After completing the development of the heavy metal detection and measurement system, the following statements are concluded to validate the objectives that were set in the Chapter 1. 1. The proponents managed to construct a floating device. It serves as the main base of the offshore. All hardware are sealed inside to avoid water from entering. A remote control is designed with an LCD screen where user can monitor the location of the boat. 2. The water sample acquisition system and spectral triad was established and implemented. It is not tested through actual simulations. A dummy dataset is built and gathered through generating random values via Microsoft Excel. 3. Not being able to perform the experimental setup resulted in lower accuracy of the device since the wavelength was not established properly for the study. 4. 3 proposed classification machine learning models were KNN, SVM, and ANN. These were trained and tested to be able to choose the best model with the highest accuracy that will be used in the system. The proponents used default and optimized parameters with 80-20, 75-25, and 70-30 data splitting. 5. The three proposed regression machine learning models were KNNR, SVR, and ANNR. These were trained and tested to be able to choose the best model with the highest R-squared score that will be used in the system. The proponents used default and optimized parameters with 80-20, 75-25, and 70-30 data splitting. 6. A graphical user interface was developed by the proponents in order to provide displays of different functions: a map of the sampling location, a small display of battery level, and an assessment of concentration level after conducting the sampling acquisition. 7. Both accuracy and reliability of the overall system were not tested due to the COVID outbreak.
The following are recommendations as observed by the proponents for further improvement of the project. 1. Use chemical reagents to eliminate the noise that the sensor may read that will intervene in the results. The reagents will further emphasize the metals that will measure and will remove the possible outliers in the data. 2. Use other spectroscopy sensors that will feature more wavelengths in the UV to visible light spectrum. The spectral tolerance sensor features only few wavelengths, which limits the possible features that may be used for machine learning. 3. Create a fully automated boat maneuvering instead of using a remote control for the movement of the boat and signaling the start of the sampling. The boat will automatically move to the sampling point as the chosen by the user and the start of water acquisition once arrived on the spot. This will help in maintaining the same location in every testing done. 4. Instead of using thermal printer, the results will be uploaded in a website that may be viewed by any DENR official where they will register their ID number for privacy purposes. This will reduce the cost of thermal paper and will help to collect data for documentation.